This week, we're talking about canonical correlation analysis. So we should all be pretty familiar with correlation by now. It's sort of the basis of everything that we do. Canonical correlation is a generalization of the correlation that we know that allows us to summarize correlations between pairs of multivariate data. So recall that in any multivariate data setting where you have p variables, you can define a new variable as a linear combination of each of the p variables. For example, if p is 3, we can define a new variable. We're going to call it u1 here as 2 times x plus x2 minus x3. And this is a linear combination of the 3 x's in the big bold x, where the big bold x is our multivariate data. So u is just a single variable that's a linear combination of 3 other variables. We could likewise define u2 as 0 times x1 plus x2 plus 0 times x3. This is also a valid linear combination, which also just happens to simplify to having u2 equal x2. The idea behind canonical correlation is that when you have 2 sets of variables, x with p variables and y with q variables, you want to find the linear combination of each x and y that maximizes the correlation between them. So if we're going to call ui a linear combination of the p variables in x and vi a linear combination of the q variables in y, we want to find the coefficients that produce the u and v with the greatest possible correlation. We'll call these linear combinations u1 and v1 the first canonical variates of x and y. Those shouldn't be bold. I'll fix that. Those should just be regular u and v because they're just single variables. After maximizing the first correlation, we can repeat this process, except now we're trying to find the maximal correlation between linear combinations of x and y that is also uncorrelated with u1 and v1. Essentially, what we're saying is that we're using all the leftover information after finding the first canonical variate to find another canonical variate. And we can keep repeating this process k times, where k is the minimum of p and q, since that's the most number of orthogonal variates we can generate from the smallest partition of our data. So whichever is the smallest between p and q, that's the most number of times we can generate an orthogonal linear combination for that that partition of the data, and so that's the most number of canonical variates we can generate. So there's a relatively simple algorithm for finding the canonical variates for pairs of multivariate data. So first we need to partition the covariance matrix of the full data with both x and y, and then we need to sort of slice it up. So we're going to take the covariance matrix of x for x. We're going to call that SXX. And that we're going to take the covariance matrix for y, we'll call that SYY. Then we're also going to get SXY, which is the covariances between x and y. So this is the sort of like off diagonal part. This won't have any of the variances. It'll just be the covariances between all the variables in x and the variables in y. And then SYX, which is the reflection of that. So it's SYX is the same thing as SXY, just reflected over the diagonal. So then we can define the variate matrix of x on y. So that is going to be defined by taking the inverse root of SXX times SXY times the inverse of SYY times SYX times the inverse root again of SXX. And we can also do that in the other direction. So we could do that for the variate matrix for y on x. And this is how we're going to obtain our canonical variates. So to make use of these matrices, we're going to take the eigenvectors of both of them. So we're going to denote the eigenvectors of the variate matrix for x on y as E, and the eigenvectors for the variant matrix of y on x as F. And we're going to order the eigenvectors by the size of the associated eigenvalues. So keep in mind also this is all sample notation. So this is as if we were working with a sample of data. If we're working with the full population, which in practice we never do, but in theory we like to talk about, we just replace the x with, or the s with sigma, and that would be the population notation. So the coefficients that represent the linear combination for each canonical variate can then be computed by transposing the eigenvalues and multiplying them by the inverse root of the associated covariance matrix. So the transpose E. So each E for each eigenvector EI, transpose it, multiply it by SXX inverse root, and so that those are the coefficients for associated with each canonical variate for X, and then for Y it would just be the F eigenvalues transposed times inverse root SYY. And so that way we get our U canonical variates for our X matrix as E transpose times S inverse root XX times the original data X. So that gives us each UI, and VI the same thing for the F eigenvalues and the Y data and the covariance of the Y data. So it also turns out that the canonical correlations between each pair of canonical variates, U, I, and VI, which we're going to denote as rho I, that's the Greek letter rho, RHO, are the square roots of the eigenvalues of either of these variate matrices. So rho squared equals the eigenvalue of either variate matrix. So let's look at an example. So this is a data set that's simulated based on the correlation matrix in example 10.5 from the book. So they don't provide the raw data for this. They just provide a correlation matrix. Uses 5 variables related to job characteristics. So these are the X variables, the first 5 variables. They're being used to predict 7 variables related to job satisfaction, the Y variables. And each variable is suffixed with either X or Y to denote which partition it belongs in. So the job characteristic variables are feedback, task significance, task variety, task identity, and autonomy. So these are the characteristics of different jobs from this data. And so these are satisfaction ratings from the workers who work in each of these jobs. So there are 7 variables here. There's supervisor satisfaction, career satisfaction, financial satisfaction, workload satisfaction, company satisfaction, satisfaction with type of work, which is work type, and then general worker satisfaction. So R doesn't have built-in support for doing canonical correlation analysis from a correlation or covariance matrix directly. Maybe something we can program, hint, but it does have several ways to do a canonical correlation analysis on real data. And to use a correlation or covariance matrix in principle, all you need to do is skip the very first step here where we obtain the covariance matrix. And then we can do everything else pretty much the same way. It also turns out that canonical correlation analysis can either use a correlation or covariance matrix. The only difference is whether the coefficients will be raw or standardized, which we'll talk a little bit more about. So here's just a preview of the data, just an idea of what it looks like. So next, what I'm going to do is get my full covariance matrix, and then I'm going to slice it up. So SXX is the X by X, the 5 X by X variables. So it's the first 5 rows and the first 5 columns. SYY is the next 7 rows and columns. So that's the covariance matrix of Y. And then I'm going to get the off covariances, the covariances between X and Y. So the rows of X and the columns of Y. And then the rows of Y and the columns of X is SYX. So now I'm going to get these variate matrices that define X, the variates for X on Y and vice versa. And so these are the formulas that we saw before. And so I'm just plugging directly into these in our code here. And so the square roots of the eigenvalues for either of these variate matrices will be our canonical correlations, the rows. That's RHO again, the Greek letter. In order of largest to smallest. So that we're only going to interpret the first 5 though, since P is 5, which is less than Q equals 7. So for the variant matrix for Y on X, we'll actually have 7 values, but the last 2 will basically just be super close to 0. They might have like a little bit of a rounding error that like makes them not quite 0, but they should just be, in theory, they're just 0. So we're just going to ignore them. So here we see that the square root of either eigenvalue for either matrix produces the exact same value. So we get the same correlations. And these are the correlation magnitudes, of course. Some could be positive and negative, but since we're just taking the square root here, we're just getting the positive roots. So these are the correlation magnitudes. So the linear coefficients we use to produce our canonical variates is the product of the transposed eigenvector matrix of the variant matrix and the inverse root of the original covariance matrix. So the coefficient is E transpose times the inverse root covariance matrix. I'm going to transpose the output to avoid confusion so that we interpret these column-wise. This will make it easier to match what we see later what we get from the R functions. So these are the canonical coefficients if we transpose the data. So this indicates that our first canonical variate is negative 0.44 minus times feedback minus 0.03 times task significance minus 0.18 times task variability minus 0.04 times task ID minus 0.51 times autonomy. And so we can see if we look down the first column, these are the coefficients for each variable that define the first canonical variate. So we could loosely interpret this to mean that the first canonical variate is being driven by feedback and autonomy. However, this interpretation only works on standardized data. So the coefficients are much more difficult to interpret on unstandardized data. You can get standardized coefficients by multiplying the unstandardized coefficient by the variable's standard deviation, or starting with a correlation matrix instead of a covariance matrix. But because everything here is based on a correlation matrix simulated from a correlation matrix, the data here is pretty much standardized already. So we can interpret these even though they're technically the unstandardized coefficients. We could do the same thing here for the second column and just plug them in and multiply them by each variable to get the linear combination of each variable that represents our second canonical variate. And we can do the same thing for y. So finally, to get our canonical variate, so these are the actual linear combinations of each variable multiplied by the coefficients, we can just simply do that. So here I'm using the matrix process to multiply each variable by each coefficient, so that each column here now is our canonical variate. So the first column here is just the first 6 rows of the first canonical variate, but this full matrix matches the original size of our original data, which is I think 784 observations. I'm just showing the first 6 rows. So we have we have 5 canonical variates here, and then we could of course do the same thing for y, although we ignore the last 2. We're only interested in the first 5. The last 2 don't actually can't be correlated with the x variables because the x variate, there's only 5 variates for x, while there's 7 for y. Well, you can only correlate the first 5. So within each variable groupings, for example, like the correlations within all of the x-based canonical variates, which I named u, are all going to be 0, and the standard deviations are all going to be 1. So we see that the variances are all going to be 1, which means the standard deviations will also be 1. But we see that off the diagonal, so the first canonical variate of x is uncorrelated with the second, third, fourth, and fifth canonical variate of x. So these are orthogonal variates. That's one of the definitions of them. And then when we correlate u with v, so these are the variates of x and the variates of y, we see that along the diagonal we get the same correlations that we got before when we check the eigenvalues, although now they have signs. So here we see the second correlation is actually negative. and then off the diagonal, we still get zeros. So this is the this would be the second canonical variate of x is uncorrelated with the first canonical variate of y. So those are all also orthogonal. But if you check this diagonal here, it matches up to what the magnitudes of what we got a few slides back when we got the original canonical correlations. And I'll just jump back to that quickly so you can see. There they are. So 0.5436, 0.2831, blah, blah, blah. So just the only difference is this one isn't negative because here we're just taking the square root. So we just got the positive roots. But that is identical to the diagonals here, or the diagonal here. So another way to interpret the canonical variates is to check their correlation with the original data. So here I'm looking at the correlation between the 5 original x variables and each canonical variate. So we see that the first canonical variate is highly correlated with each of the individual variables, though it has the highest correlations with autonomy and feedback. So that sort of matches up to our result from before, where the coefficients were largest for those. And so the second seems to be more correlated with task significance and task variety, and a little bit with autonomy, not much with task ID or feedback. And we can do the same thing for y, of course. Look at the original y variables and see their correlations with the canonical variates, and the interpretation is the same. So the first variate seems to be correlated with supervisor and work type, a bit with career and company, and then a bit less with finance, workload, and general satisfaction. So we see the highest correlations are with, the largest correlations are with supervisor and work type. Then the next highest are with company and career, and then they're a little bit lower. They're still fairly high with finance, workload, and general. And so we can also test the significance of our canonical variates. So we can define lambda as the ratio of the determinant of sxx times the determinant of syy divided by the determinant of the full S, which has both x and y in it. So the logic here is that if sxx and syy, or if x and y are independent, this ratio will approach 1. Which essentially means that the off diagonals are going to be zeros. So the covariances between the x and y variables are zeros. And we can use lambda to test the null hypothesis that the off diagonal elements of the population covariance matrix are 0. It also turns out that this is equivalent to the product of 1 minus each of the canonical correlations squared. So this is also equivalent to testing the null hypothesis that the first canonical correlation equals the second canonical correlation equals all of the canonical correlations equals 0. And so this is a general test of all canonical correlations, but since the canonical correlations are ordered from largest to smallest, it's really just testing the null hypothesis that the first canonical correlation is 0. Since if the first canonical correlation is 0, all of the subsequent ones are also going to be closer to 0 than the first one, so that we won't be able to reject the null hypothesis for any of them. So we could take advantage of this logic and do an iterative series of tests where if we reject the null hypothesis that the first canonical correlation is 0, we then delete the first canonical variate and redo the tests on all the remaining canonical variates. And then each time if the test is significant, we continue to repeat the process. If we reach a null hypothesis that we retain, we can stop, since we know that all subsequent canonical correlations will be smaller and will also retain the null hypothesis. So as before, the book gives a chi-square approximation for testing lambda, or for just doing this test in general, where you are testing the kth canonical correlation. So R is smarter and gives us an F-test, which is a bit more precise, but the degrees of freedom are more difficult to specify. So there is no established way to correct alpha for a multiple comparisons test like this. We're testing several correlations based on orthogonal variates, and so there isn't like just a Bonferroni adjustment that we can do to get the correct alpha here. So this is really more of a loose guideline than a hard statistical test. We will have an inflated type 1 error rate, technically. So this should really just be more of a loose guideline than a hard test, as I said. So using R to do all this, of course, is much easier than what we just saw, as always. R has a default can-core function for canonical correlation, but its output isn't very nice, and it does some weird scaling of the coefficients. I think it just automatically standardizes everything, it may have a way to give you the raw unstandardized coefficients too. I'm not 100% sure. I have to check. But there's a nicer one from the CanDisk package called. It's just also can-core, just overwrites the can-core function. It's designed to be a companion to the Heplots package for doing data visualization and other stuff. But it's just a nicer function. It accepts formula syntax, which can make our life easier a lot of times. And it outputs significance tests as well, as we just defined. So here I can run a canonical correlation where I have all of my y variables on the left-hand side of my my formula syntax, and then my x variables on the right-hand side. The summary output is going to give us, I don't know why it prints like this in our Markdown, but the screenshot is from when you do this in R looks like this. So you see that the first thing that it gives you is the null hypothesis for the canonical correlations of the current row and each row that follows. So, so this is the null hypothesis that there is either the first row or all subsequent rows are 0. So we reject the null hypothesis. We reject it for the second row as well, but we do not for the third. So once we get to the third row, we know that after the third correlation, all the other ones are going to retain the null hypothesis as well. So we can also extract the coefficients for our canonical correlation with the coef function by specifying x, y, or both. We can, again, loosely interpret this to mean the first canonical variate about job characteristics is driven by feedback and autonomy. Again, but in this case, the data is already nearly standardized since it's based on it's simulated from a correlation matrix. In most cases, raw data won't be. So to really get interpretable coefficients, you need to standardize them. And you can do this with a standardized equals true argument. And you see that it really doesn't change the results in this case very much. It's a very, very slight change. But these in most practical settings, these would be much more easy to interpret. And we'll see an example of this later. And here we can do the same for the y. And we could also get the canonical variates, u and v, with the scores function. These are scaled very slightly differently than the results I got before, and I'm not 100% sure why, but I'm not too worried about it. It's still all the other results still hold up, as we will see. The correlations with the original variables, as we checked before, are still identical. This is the same result that we saw before, where we looked at the correlation between the canonical variates and the original variable. So we can see that first canonical variate here is correlated most highly with feedback and autonomy, but also with the other 3x variables. And there's that interpretation, again, just for reference.